带我去星巴克。带我去星巴克。
Okay.
我准备好了。
确认。
开启智能驾驶吗？
Our next generation interactive driving system, powered by BLA models. The user just simply say, 理想同学 take me to Starbucks. 理想同学
感
is
谢乘坐
our
理想传送巴
great
士，
friend,
请带好随
just
身物
like
品，
we say
期待
Hey
下次再
Siri
见。
in Apple. This vehicle can automatically navigation to the nearby Starbucks itself without any driver in the seat. So this is the production feature, not the test mode. It can currently available on the private campus and the internal road in China, according to the local regulations. How we evolve to this point? This is our LEAD tech roadmap. Before 2023, our system relied on many modular rule-based algorithms with small learning modules inside each block. The blue block is the learning-based block, and the gray block is the pure algorithm block. And we find the progress is slowly because the performance bounded by the manual behaviors and engineering effort. And then in 2024, we came out proves the dual system, combining end-to-end and the VLM model, letting the system learn direct from the sensor to trajectory. The progress and proved, and by the data scale and the quality become the key importance. And by 2025, we saw imitation gains plateau. So in September 2025, we introduced the VLA, the right one, the VLA model, integrating the reinforcement learning and a training closed loop architecture, that will be making the training efficiency into the new driver evolution. Let's revisit how the data closed loop in dual system work. This is the data closed loop. A data closed loop is continuous capture on the road events, labels the right samples, and retrain the model and redeploy them and collect the next data. It forms the self-improving circle. The Lioto has built this loop at 2019. So enable car to cloud uploads and automatically trigger to interesting events. There are three key metrics in our closed loop system, data closed loop system. The first one, we have the 1.5 billion kilometer of driving data. Maybe this is among the largest industry data set globally besides Tesla. And we have the more than 200 triggers that can trigger 15 to 45-second all data clips, include 11 camera data and high beam LiDAR sensor. So, and we have a very quickly feedback about the closed loop data system. And we can upload the latency if you put the upload the button, and we can receive the data less than 1 minute. The faster feedback and the model will iteration faster. So what does the data closed loop achieve in progress? Building by the data closed and our end-to-end plus VLM system, we observe the clearly scaling law in data. And the larger, the higher quality data set yields stronger and stronger driving models you can use in the system. This chart shows MPI. MPI means the miles per intervention. This chart, it shows MPI in the rising about 20 times from the mid-2024 to the mid-2025. and our data clips grow to 1 million to 10 millions, from 1 million to 10 millions. Yeah, the raises a crucial question that the data closed loop can reach level 4 in autonomous driving. Let's see how hard the real world is. The real world, I think, has very, very sparse events. And the naturally events may be some sparse. So we can impossible to cover every real or the composition real event by just a human collection. Let's see some examples. The first one is the traffic officer gestures. You should know what the hand signals and require causal reasoning and not just the pattern matching. And the middle, the fireworks is exploding. So you need to know how to avoid the fireworks and how to avoid the smokes. And third one, a ship ahead of ship is suddenly cross the world. You should know this is non-rigid nature and how to react quickly and safely. It's not easy. This illustrates the edge corners we must handle. So this is the level 4 autonomous purpose. So how to go the next generation in the broader AI fields? In the AI research, some scholars like Shunyu Yao and Richard Zhan have described the second half of AI, and they propose the area of experiment learning. The Shunyu Yao said the second half of AI will be about evolution, environments, and real-world utility. And Richard Zhan said a new generation of agents will occur superhuman capabilities by learning predominated from experience. So they also mentioned the 3 words: evaluation, reward, and environment. So how to use this transition to the new autonomous driving shaping? So we think we need to go to the second half in autonomous driving, from data closed loop to training closed loop. The training closed loop, we think it may go beyond the just collecting and develop a deployment. It lets the model interact with the environment and generate a new experience and receive feedback or rewards on the defined objectives. The key idea, we think, the progress is driven by a goal, not just by data volume. The loop is continued until the objective is achieved. For example, you need to set the higher safety score, or maybe you have the comfort tracing, and you can get the simulation score internal. You need to achieve this score, not just run away about the data. So let's see how we build this loop in the practice through VLA and world model. In the auto, our approach appeals on the on-device VLA model that is trained by the driving data trials. And right, we have the uncloud-based world model environment. The world model contains a real world, synthetic world, and the dynamic explored experiences. Through the reinforcement learning framework, such as RHF, RHVR, verified reward, and RLAF, that can learn this can train the VLA to the objective. This forms a large and integrated system linking environment construction, agent behavior, feedback mechanism, and scenario simulations. So let's look at the technology stacks behind our world model. The world model is the key of the L4 training loop. The auto world models are built on 3 functional pillars, the top 3. The first one is a regional scale simulation. that can evaluation and testing our on-device models in long horizon and high fidelity environments. And second is the synthetic data that can create diverse things to cover the real cases. And second one is the reinforcement learning that can where the model can actively explore and learning by feedback. And we to achieve these three goals, and this three goals is harder one by one. We need to achieve these three goals. We have the scene reconstruction, multi-sensor rendering, and multimodal generation, traffic agent, 3D assets, and so on. And the last one is system efficiency, especially in training and inference. It is the core bottleneck of how to develop at scale. So the training efficiency acceleration is important. And in these three pillars support these three pillars support our L4 training closed loop. So let's see how to dive into how to build this environment. First, the auto world model combines the reconstruction and the generation. How to illustrate the difference? Use myself, for example. This is myself picture and taken by in the hotel lobby. And to reconstruction, we can reproduce the geometry and the texture precisely. The clothes is exactly right. And the picture is consistent and stable, but just static. But we can generate it by the model using the generation. We can build a generation image. And also, we can build a generation of video. You can see that it's modified by scene and diverse and dynamic. Both the essential reconstruction issues fidelity. Generation brings convergence and controllability. So how to hybrid the approach can evolve in our system. Since NERF emerged, many teams have adopted reconstruction-based method to accelerate simulation and narrow the domain gap, while the traditional tools like Color or the Unreal Engine. At the Auto, since 2023, we have worked with Professor Sapong in Zhejiang University and applied the 3D Gaussian splatting to the large-scale driving scene to reconstruction. But pure reconstruction proved limited. So we shift to the hybrid paradigm, reconstruction plus generation, combining stability with the generation. Now, with the feed-forward 3D method such as VGGT, we're developing the next generation rendering method, system emphasis generation capability. How several our key reconstruction work and our work to impact the industry. First, we will introduce the reconstruction work. About the 2023, we first bring to 3DGS into the autonomous driving simulation, and we can take the scene build latency with very small latency to build the simulation in our internal system. And then 2024, we have built the 3D real car data set. It contains 2,500 realistic vehicle models internal. We public released under the Apache license 2 and have downloaded to about more than 2,000. And third one, we have built the balanced 3DGS with NVIDIA. We have the 7 times faster training and rendering on GPU. And this year, and it accepted by ICCV25, this conference. We build a scalability city-level reconstruction for autonomous driving evolution. And this work is also adopted in our internal system. Next, we will introduce the generation and how to combine with the reconstruction. The first work is the Recon Dreamer. In the November 2024, we add the view supplementary generation to boost the novel view synthesis quality while keeping the real-time rendering. And the March 2025, we propose the style street. It can extend 3D-GS to multi-style rendering of the same scene and enriching the diversity of the scene generations. And next, we have a fully controllable generative model conditioned by the 3D geometry and per frame and has a very consistent depth in the scene generations. Together, we from our reconstruction and generation hybrid stack, linking scene realism and creative diversity. Now, let's look at the pure generating work. Most generative methods still rely on reconstruction data from the 3D geometry supervision. And as the reconstruction proves, the generation work gains strength. The first work is the driving sphere. It will be accepted by ICCV25, a controllable generative framework using an occupancy reconstruction. You can predict next frame occupancy, and through the occupancy, you can build the next video and the LiDAR. And next one is OmniGen. We support more large-scale multimodal synthesis across the driving scenarios. And now we have proposed the RLGF accepted by NIPS 2025 and use depth consistency as feedback for the stable outputs. Fourth generation model. Industry development still faces challenges in stability and efficiency, but it is a clear and right long-term directions. We continue collaborating with top university to push it forward, and we will move to the simulation, from simulation to the synthetic data. So, synthetic data is emerging as a core competitive factor to the next generation of system. By active generating new data and balancing through the synthetic evolution, we can unlock the full potential of the large driving models. We think there are three main application levels. The first is the scene editor. You can see these two videos. The right one, we have inserted the traffic cone into the road, and it's very realism. And left one is the original video. So we can edit this scene to challenge more data and challenge to more model behaviors. And second one, we can use the scene transfer. It can extend real scenarios. The ETC, the tour gate is a real thing, and the reverse vehicle is also the real thing. The composition real thing is hard to collect it. The left one is the original video, and the middle one we can transfer to the raining and the dark scene, and the right one we can transfer to the snow. And the third, we can also forcing generations. We can generate entire the camera plus LiDAR sequences just from text prompts or 3D box or the lane or the traffic lane. Fully generated data still struggle with temporal coherence and sequence length, but the progress is very accelerating. So with this data generation method, how does it improve our data distribution? With word model-based synthesis, our data distribution becomes more balanced. The top chart shows that this is the original real-world data distribution. It's very unbalanced, such as whether most data is in sunny. And the bottom chart shows the balanced version after incorporating synthetic data and target sampling. We can clearly see the improvement coverage between the road environment and talked vehicle scenarios. As the generated quality rises, we achieve the finer control over dataset composition, leading to the stronger model ability and generalization. Let's move to the final but most challenging part, reinforcement engine. Unlike the simulation and the data generation, reinforcement learning engine demands real-time generalization and massive concurrency, making it hardest stage of our closed loop. We decompose the RL word engine into 5 components. The first is the word model. It can build environmental realism. And second is the 3D asset that can add the scene diversity. And third is simulation agent. It can make the interactive behaviors. And fourth is the reward model. It can give the exact feedback and human preference. The last is the system performance optimization. Among these, we talked about the word model and 3D assets. The simulation engine are both the hardest and the most critical problem. The reward model achieves the learning signal, and the system performance achieves the scalability across the GPUs in the infra. Let's look deeper into interactive agents and why they matters. Modeling other vehicle behaviors and interacting is very harder than single vehicle autonomy. The left one, industry-wide, this year, Apple have proposed a self-play paradigm. I think that is a very powerful framework to multi-agent learning framework. In our system, we can also design each agent specifically goals and using the specific goals and reward to control the individual and the interactive dynamics. The last video, we can use the blue star is the goal point. They can change the blue star, the agents have the different interactive behaviors. Internally, our project MAD focuses on multi-agent diversity. We'll plan to open source it in the future. Now, watch the right scenarios. The Eagle car performance on the unprotected left turn, and the case above, the surrounding cars keep the same velocity by the locked recorder. And the case below, they react dynamically, producing much more natural interaction. So let's zoom in. Okay, this one is above video with no smart agents. So the locked agent case, the Eagle vehicle, the right one, the Eagle vehicle received the penalty and discouraging risk moves, and show the surrounding agent behavior will directly shape the Eagle model's reward value. To ensure the robust training, the distribution of other agents must match real-world driving statistics, not too conservative and not too aggressive. The right picture is with smart agents, so the active behavior is more safer. This remains an open research challenge, and we will very welcome collaboration from the community to push it forward. Okay, just in 2025, our autonomous driving team has published over 18 papers at a top layer conference like CVPR, ICCV, ECCV, NIPS, ICRO, and so on. Our research have expanded from traditional perception and end-to-end tasks to the new frontier topics such as VLM, VLA, world model, and reinforcement learning. We sincerely welcome collaboration and open discussion with persons in academic and industry. So let's summary. To summary, we believe in the future, autonomous driving will evolve from the data closed loop to the training closed loop, where learning become goal-driven, experience-based, and build around autonomous exploration and continuous feedback. This transition from the collecting data to active learning from the experience, in our opinion, is a key pathway towards fourth scenario level for autonomy. So that's all. Thank you very much for your listening. I'm happy to talk about your question and discuss further. Thank you.
If you have any questions, please raise your hands and we can yes. Hi, thanks so much for the talk. I was wondering if you could just share a little more detail about the reward model and human feedback, how you sort of set those guidelines, how you kind of define good driving versus bad.
You see how to define the word model, the feedback, right?
Yes, just
Okay.
Any detail you can share on how you trained the reward model, what the supervision was, like this.
Okay, this is a good question. Yeah, we have the reinforcement method, RHF, and using the human feedback and RHVR and the verify reward. The verify reward is the simulation score. Such includes all the aspects about the driving, just like the navigation and the safety and the efficiency and the comfortable and so on. So this is the RFVR. And we also built on the RLAIF reward model. The reward model is a very huge parameter models to just predict the behavioral score. That score can predict how can explore the environment. So this is the three method to train our model in the environment. The human performance, human preference, we can using the user cases when the intervention the driver, so we can collect the human preference. The verify reward, we can use the simulation score and the AI reward and to build with a large language model. Yeah.
Thank you.
Maybe it's a high-level question. The reinforcement learning loop, is it limited to the simulator world or you connect process to actual driving?
Okay. We think the reinforcement learning maybe have some gap in the real world and the simulation world. But we think in the traditional system, we have the two parts of the domain gap. The first one is the environment. Maybe when we use the color, we cannot transfer the model building color to the realistic system. And the second one is the simulation smart agent. That's important. So we think in this area, we almost solve the environment problem by the 3GS and the generation model that can build a very realistic and the diversity scenarios on the cloud. But it's hard to build a very smart agent to interactive with the ego vehicle. It's still the hard problem. So we still move on and we figure out that question. Thank you.